Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, welcome everyone to this next session. We have two papers in this session. They'll both be 15 minutes each. And we're going to carry on sort of the first part with this theme of optimization, but from a very different kind of view. So for the first talk, we're going to hear about probabilistic line searches from Maren Massarici from the Tübingen MPI.
Thank you very much. All right, so the general setting is nonlinear optimization. We want to find a local minimum x star of a potentially very high dimensional function f of x. Now, typically, an optimizer would keep around an estimate xi of that local minimum, and then update it iteratively by greedily descending. So at every step, the optimizer chooses a search direction S in which it wants to step. And then, conditioned on that search direction, it adjusts a step size t, which defines the length of the step. So there is a lot of practical work going into finding good search directions. But it is equally important to also adjust good step sizes because they crucially affect optimization performance as well. So for example, in deep learning, these step sizes are called learning rates. Now in deterministic or noise-free optimization, there is a well-known paradigm that automatically adjusts these step sizes, and they're called line searches. So we will quickly skim over a typical workflow of such a line search. Every line search starts with an initial function and gradient evaluation at the current position of the optimizer. So the top plot shows function values, the second plot gradients, and the initial evaluation is already plotted on the left. And on the x-axis, there's the step size. So the line search now tries to find a good or appropriate point on the positive x-axis. Now, acceptability or appropriate point is encoded in two inequalities called Wolfe conditions. They're written on the bottom of the slide, and they monitor the decay. So the first Wolfe condition on the bottom left, labeled W1, imposes linear decay on the function values, and the second Wolfe condition on the bottom right exists in two versions, a weak and a strong one. And the weak version only accepts points which gradients are larger than the initial gradient, and the strong version only accepts points when the gradients are flatter than the initial gradient. So in the plot, the weak and the strong versions of the Wolfe condition, or the acceptable regions of the weak and strong Wolfe conditions, are shown as light and dark green shaded areas. So if a point lies inside of the green shaded area, then it will be accepted by the line search. All right, so now a typical workflow is quite straightforward. First, the line search proposes a point, for example, at this vertical red line. Then it evaluates the point there, and it checks on the Wolfe conditions. So this point does not fulfill the Wolfe conditions, but the gradient is still very negative. So it excludes, like the line search excludes the whole search space to the left of this point, and is looking even further to the right at this vertical red line. Then it evaluates the function again. This point also does not fulfill the Wolfe condition, but this time the gradient is positive, so it excludes the whole search space to the right of it, and makes a cubic interpolation in between the last 2 points. So the next candidate point would be at the local minimum of this cubic interpolation. The line search evaluates the function again, and there we go. This point indeed fulfills the Wolfe condition and would be accepted by the line search. So this is also the point now where the optimizer is going to step to next. All right, so in summary, many classic line searches model the one-dimensional objective with a cubic polynomial. The search for candidates is done by excluding complete regions and collapsing the search space. And points are only accepted if they fulfill the Wolfe conditions. This works really well for noise-free deterministic optimization problems, but it fails as soon as we introduce stochasticity. Many machine learning problems, though, are noisy. For example, if we have an exchangeable loss function, which is a large sum, and we approximate it by a smaller sum. So this is actually the thing that Asu Özdalar just talked about, exactly that loss function. And now this estimator for our loss function and its derivative is approximately Gaussian distributed. Now with this knowledge, we can try to extend the line search paradigm to the noisy or probabilistic setting. Due to the Gaussianity, we're going to assume a Gaussian process as surrogate for our one-dimensional objective. As search for candidates, instead of excluding regions and collapsing the search space, we will leave the whole search space open and do Bayesian optimization. And third is acceptance criterion. Instead of having binary Wolfe conditions, we're going to have a probability that the Wolfe conditions are fulfilled. So these three steps in more detail. The Gaussian process we're using is an integrated Wiener process. This is a very nice kernel. It is robust and flexible, and the posterior mean are piecewise cubic splines which have analytic minima. And this is a feature that we're going to use as well in the next step. So for the search of candidates, we do Bayesian optimization, and we use a well-known utility function called the expected improvement. Now, instead of optimizing the expected improvement globally, we will only evaluate it at a few well-chosen candidate points, which are the analytic minima of the posterior mean and one extrapolation point. And then we are going to choose in between these. All right, now as acceptance criterion, the important observation here to make is that the weak Wolfe conditions are in fact positivity constraints on two variables A and B, which are linear combinations of function values and gradients. Now, since we implied or imposed a Gaussian process on function values and gradients, this map implies at each point t a bivariate Gaussian distribution over A and B. Now, for the weak Wolfe conditions to hold, A and B must be positive. So the probability for the weak Wolfe conditions to hold is the integral over this probability density over the positive quadrant. All right, there is also a straightforward approximation to the strong Wolfe conditions, and it basically does exactly the same computation, but it exchanges one limit of the integral. All right, so with this machinery at hand, we can now look again at the typical workflow, this time of a probabilistic line search. It also starts with an initial function and gradient evaluation at the current position of the optimizer. The top plot shows the marginal belief over function values, and the bottom plot marginal beliefs over gradients. And again, the initial evaluation is already plotted. Now, the line search proposes an initial candidate. It evaluates the function there, then it updates the Gaussian process. And now at the bottom, you can see an orange Gauss blob in this red box. And this Gauss blob is the probability density for the Wolfe conditions. So we will accept the point if at least 30% of this probability mass lies inside of the green shaded area. So this point clearly does not fulfill the Wolfe conditions, so it will be rejected for now. The line search proposes another candidate point. It evaluates the function there, then it updates the GP, and again it checks the Wolfe conditions. So also the Gauss blob of the blue point does not lie sufficiently inside of the green shaded area, so it will also be rejected for now. For the next candidate points, we in fact have two of them. One of them being the local minimum in between the red and the blue point, and the other one being one more extrapolation point. So now we want to choose in between them where we want to evaluate next. And this is done by the solid dark blue line. The solid dark blue line is the product of the expected improvement at every point times the probability that the Wolfe conditions are fulfilled at every point. And in fact, we don't compute this blue line at every point, we just compute it at the positions of the candidates. And then we choose the one with the highest value. So for our candidates here, the one on the left wins. So we evaluate there. We update the GP again. And now we accept the green point because about 70% of the Wolfe probability density lies inside of the green shaded area. All right. So we tested the line search on two different architectures of a two-layer neural network in combination with stochastic gradient descent. One network being on cipher 10, which is on the left side of the slide, and the other one being on MNIST, which is on the right side of the slide. Now, top plots show test error versus initial learning rate after 10 epochs. And so this is basically performance, and the lower is better. Now, every plot shows two curves. The light gray one with the X markers is SGD with a fixed learning rate, and the dark gray horizontal one is SGD governed by the line search. Well, there is a qualitative difference in between the two curves. The performance of SGD with the fixed learning rate is dependent on the choice of this learning rate, and the SGD or the performance of SGD in combination with the line search is not. So for different choices of initial learning rates, the line search controls these learning rates and yield similar good results. Now the bottom plots show test error versus epoch. So this is evolution of performance in time. And the left plots respectively show SGD instances with fixed learning rate. Different colors are different learning rates. And again, they vary in a high range and the performance is highly dependent on the choice of it. While on the right plots respectively, the instances governed by the line search bundle up very nicely, and independent of the choice of the initial learning rate, all yield comparable results. All right, so there's a lot more to say about this, a lot more theory to talk about. If you like, please meet us at poster number 40 this evening, and thank you very much.
So if there are any questions, then maybe we can just get ready and wave your hands. But I'll actually start with the first question, actually. So we choose the cubic interpolance spline because it has these good analytic properties that make the whole algorithm linear complexity effectively. So you use this, the Wiener kernel, that's because it makes a order n, O(n) complexity algorithm. So that's for computational reasons. Are there other reasons you would use that give you particular robustness to outliers in the gradient estimators, or other kinds of kernels that we might want to use?
Yeah, so we don't use the kernel for the complexity reason, because if you think of complexity reasons, the GP, if you think of cubic complexity, this does not matter in this case because our GP is very tiny. So we're just inverting a 4x4 or a 6x6 matrix, and this is virtually it's very inexpensive in comparison to actually evaluating a gradient. So this is not the reason. The reason is really that this kernel has very nice properties in comparison to, for our purposes, very nice properties. And it is also, for now, the straightforward extension to what a classical line search does.
Anyone else wants to ask a quick question? No? Okay, next time, Maren again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.